Smell is one of nature's most important sensory systems. For animals, it enables survival, helping them find food, detect danger, and track hidden targets. Humans, however, have only limited olfactory ability, which makes us vulnerable to invisible threats in our environment. A critical example is indoor mold. Mold releases volatile organic compounds, or VOCs, that create distinctive odors, and it can grow in damp spaces where it poses serious health risks. Yet detecting mold is not straightforward. At low concentrations, its odor is difficult to sense. As a result, traditional detection still relies on manual inspection and sampling, followed by laboratory analysis such as GCMS or culture tests. This process is slow, labor-intensive, and limited in coverage, often taking days before results are available. Researchers have also tried electronic noses, or e-noses. These devices can identify mold in controlled conditions, often by sampling sealed bottles to concentrate VOCs, but fall short in real environments where VOC levels are too low. Moreover, e-noses cannot directly reveal where the mold is located. We introduced Scensory, a robot-enabled olfactory system that simultaneously identifies fungal identity and localizes their spatial origin using affordable sensor arrays and deep learning. Our key insight is that temporal VOC dynamics encode both chemical and spatial signatures, which we decode through neural architectures trained on robot-automated data collection. Each array combines metal oxide semiconductor sensors with a formaldehyde detector and environmental monitoring sensors, all integrated on a custom-printed circuit board with wireless Bluetooth communication. The system operates in two modes: a passive multi-array configuration using 6 spatially distributed arrays for environmental monitoring, and a mobile single-array configuration for active source tracking. To ensure precise and repeatable sampling and maximize data efficiency, we designed our automated collection platform so that the same dataset can train both sensing paradigms. In the multi-array mode, 6 spatially distributed sensors capture VOC signals simultaneously. For the single-array mode, we transform this same data by converting global coordinates into local reference frames for each sensor, simulating what a mobile robot would experience during deployment. We evaluated our system across 5 phylogenetically diverse fungal species, where each prediction takes only 3 to 7 seconds of sensor input. In the multi-array configuration, the system achieved up to 89.85% accuracy in species identification and up to 87.31% accuracy for spatial localization across 4 directional quadrants. For mobile deployment scenarios, the single-array configuration achieved species classification accuracy ranging from 60% to 80%. While directional inference proved more challenging at 48% to 69% accuracy, this still represents meaningful spatial information from temporal VOC patterns alone. The single-array mode also enables distance estimation, achieving mean absolute errors of 11 to 13 centimeters, which is sufficient precision for practical mold remediation tasks. We demonstrated real-world feasibility through deployment on a mobile robot in a residential environment. The system successfully completed autonomous navigation and source localization without environmental recalibration, establishing a practical workflow for robotic olfactory perception in built environments. Scensory enables real-time, spatially aware fungal monitoring and builds a scalable and affordable framework for autonomous environmental sensing. This technology bridges the gap between chemical perception and spatial inference, advancing environmental health monitoring and robotic inspection capabilities. For more information, please visit our website.